everybody. Thank you for joining us on this talk. We have Dr. Gabe Shu today here with us. He's an associate professor, engineering department at the University of Alabama in Huntsville. Today, he'll be giving a talk that will provide an introduction to plasmas, what they are, what makes it unique, and the different application and uses for plasmas. And so without further ado, go ahead, Dr. Shu.
Thank you, Laura. Hello, everyone. So the title of this talk, it's a little bit long. Trying to find a nice, short, succinct version, but I just couldn't come up with it. So it's called Plasma, the Fourth State of Matter that affects our everyday lives, but no one knows about it. And when I say no one, I generally refer to the general public. So the point of this talk is to give a brief overview of what is a plasma, how it differs from our everyday knowledge of solid, liquid, and gases, standard three phases of matter, and what are some of the things that it can be used for that develop technologies that may affect us, right? And this is sort of skewed particular to the things we do within CP2AL, which is the NSF score plasma research program within the state of Alabama. But I think we cover a pretty wide spread of different plasma research areas. All right, so what is a plasma? All right, so I grew up as a kid in the 1990s, and if you were asking what a plasma is, this was the answer I would give you, right? So Halo plasma rifle, Star Trek, Star Wars, StarCraft, lots of Star in there involved, but it's not really these as of yet, right? Science fiction and movies are sort of more advanced than actual technology at this point, but maybe we'll get there one day. So more likely, or where plasmas really are, is actually these type of examples, right? So you have the sun. The sun is a giant ball of plasma. Well, stars in general are giant balls of hot plasma. You have the little plasma globes you might see in Science Museum, little plasma jets, lightning, plasma thrusters for satellites, plasma arc welding, and neon signs. These are all plasmas in different states, and you can see for very different application purposes, and both natural as well as man-made. So now, how do you get a plasma? So I borrowed this from a online webcomic called XKCD. It's very amusing, so you should go look at it. So in this little comic, they ask the question, what happens if you throw a baseball near the speed of light? Or in other words, what if you give it a lot of energy, right? And a lot. To move something to the speed of light, you have to give it a ton of energy, right? So before it's 80-mile-an-hour fastball, and then you throw a 0.9 speed of light or 604,000 miles per hour fastball. All right, so a lot of energy. So what happens is in the comics it says the ball is going so fast that it superheats the air in front of it, superheats the ball, turning the air into a plasma, turning the ball into gas, then into a plasma, essentially making everyone have a general bad day. All right. So the moral story is don't throw stuff near the speed of light, but also that plasmas are created when stuff gets really hot, right? When you add lots of energy to a substance, specifically a gas, and that gas starts losing charged particles and start becoming a plasma. So now for a more textbook definition, what is a plasma? So this is from a textbook by Francis Chen. So it says a plasma is a quasi-neutral gas of charged and neutral particles which exhibits collective behavior. So here's the three kind of important phrases that in this definition is quasi-neutral, charge or charged particles, and then collective behavior. And I'll talk about which each of these mean in the next few slides. So how do you get a plasma, right? Like I said, with the baseball example, you have to add energy to something. Typically, we create plasma from gases, right? So it could be air, hydrogen, argon, helium. And we add energy or heat to the molecules of the gas. And there are different ways to do it. But for example, here, we have a neutral atom in the black dot and then an electron. So a single electron with negative charge in the blue dot. And then we somehow add energy. Right? Could be by electric fields, could be by laser, it could be just by really hot oven. Right? That addition of energy causes the electron to hit the atom with sufficient force so that you get energy transferred. Kind of like if you, throw a baseball against the wall, and then that causes the neutral atom to lose one of its valence electrons, right? One of the electrons in the electron shell. And so that neutral atom loses a negative charge. So now it becomes a positively charged ion. And then now you have two negative electrons floating around. And then those two negative electrons can collide with two more neutral atoms to give you a total of 4 electrons, which then collide with 4 atoms to give you 8 electrons, and then it keeps cascading, so on and so forth. Right? And this rate of production of charged particles, ions, electrons, can be sort of captured in what's called Sahas relation, which tells you the ratio between the ion electron density to the neutral density is some function of temperature, right? So that's our energy term, how much energy is in the system, a constant, and then how much energy it takes to remove an electron. Right? So you can think of ionization kind of like a chemical reaction in a sense, where there's a certain amount of barrier you have to overcome in order for this to happen. And then it's kind of a function of how hard you hit the molecule. So let's take it into maybe an actual experiment where we have a vacuum chamber. Right? Most plasma tend to create it in low pressures, vacuum chambers. So we have a vacuum chamber and we filled with some neutral gas. Let's call it argon gas. If we apply an electric field, in other words, external energy source across the gas, it will rip off the electrons and you'll get separate electrons and ions, let's say plasma. But there will still be some neutral particles in the gas because it's rather difficult to remove all ions and electrons. So now we get to definitions. So quasi-neutral. So as the term may signify, it's sort of neutral. What quasi-neutral means is on a large scale, large actually being somewhat of maybe centimeters scale, there are approximately the same number of positive charges as negative charges, such that the whole thing, if you take all the plasma in this box, this chamber, it can be considered neutral just from the standpoint that you have the same amount of plus, same amount of minus, right? But if you were to look at any one given small area, if you draw a tiny circle, like right here, you'll see that it's not quite quasi-neutral. So on the very small scale, maybe microns or millimeter, it may not be neutral. Those separate charges on the small scale not being neutral or quasi-neutral means that the different charged particles, the positive ions, negative electrons, can be moved by electric fields, right? So we know that negative things are attracted to positive and positive things are attracted to negative things. So that we can apply electric fields to move a plasma, if you will, or to apply forces to it. And also likewise, we can apply magnetic fields to influence the plasma as well, right? So this gives us a measure of control on plasmas that we don't get with the pure neutral argon gas. So collective behavior, because of the charged particle existence and the fact that positive and positive particles will tend to repel each other, likewise negative and negative particles repel each other, while positive and negative particles will want to attract each other, that causes a electromagnetic coupling between them, which allows them to one particle to affect its neighbors at a much longer range. And so by essentially shown here, by poking, if you will, the plasma at one region, the effect can be transferred to further in the plasma to the rest of the plasma, which allows you to have long range reach, and thus what's called collective behavior. And that's kind of one of the hallmarks of a plasma. So the plasma state, how we get it, like we said, is add energy to things, right? So here's our 3 standard states of matter we're familiar with: solid, liquid, and gas, right? So in this example, it uses ice or water. So ice is a solid water, right? Solid state when it's cold, low temperature, when it's cold, low energy. If you heat it up, you get water. If you heat it up some more, add some more energy, you get steam, so gaseous water. If you keep heating it up or adding energy, you'll start usually breaking up the water into its constituent atoms of oxygen and hydrogen, and then you'll start ionizing it into hydrogen ions, oxygen ions, and free electrons. You get a plasma state out of it. Now, this chart over here kind of shows you the range or extent of plasmas. Plasmas are typically characterized in number density, basically how much charged particles there are per volume, and then how hot they are, how energetic the particles are. So at the high end, at the very dense and high end, you have fusion and stars. Right? So these are very hot, very dense, energetic plasmas. At the very low end, you have things like flames, which, so temperature here is relative scale, right? To us, our everyday lives, flames and fires, we think is pretty hot, and it's true, it's pretty hot to us. But on the scale of plasmas, a flame is actually very low temperatures, at least compared to, say, fusion that occurs within our sun. Right? And then so there's a range of things that happen from neon signs, which we use on Earth, to lightning, which is a natural phenomenon, to interstellar nebulas. Right? So there's a wide range of plasma states that you can get. And they're all very interesting, very different, but all follow sort of the same level of same types of physics. All right, so what is kind of the useful difference between a normal gas and a plasma or plasma gas, right? So to go from normal gas to plasma, you add energy and you bump off at least one electron. So you get a positive ion and then a free negative electron, right? So in a normal gas, you will have chemical reactions, right? So for example, if you can, through electrolysis, which is if you put electrodes in water, you can break H2O water molecules into hydrogen and oxygen, right? Or if you go the other way, if you burn hydrogen and oxygen, you can get water, right? Which is how you get rockets, engines. So those are chemical reactions that just are reactions between the neutral atoms, neutral molecules. When you have a plasma state, you get those same neutral chemical reactions, but you introduce at least two new interacting species, the negative electron and the positive ion, and those interact with the other particles in different ways. So you get a host of new electron ion based reactions. And because you can more directly control these charged particles with electromagnetic fields, it gives you interesting knobs to turn to affect the chemical reactions. Right? So plasma chemistry is a very important field of application and research. So from a mathematical standpoint, a normal gas tends to follow what's called the fluid equations, right? So this is the conservation of mass, conservation of momentum, and conservation of energy, right? And go to a plasma, you still have all those because the plasma is generally still a gas, just a gas with extra stuff in it, extra charged particles. So you still have the conservation of mass, momentum, and energy, but because you have charged particles, you now have to account for the behavior of those charged particles. So you have conservation of charge, you have then what's called Maxwell's equations, which are these four Gauss's laws, Faraday's laws, and Ampere's laws, which makes a plasma much more mathematically complicated and I like to say messy than a normal gas. Right? So it makes it a bit harder to kind of study compared to a normal gas. Now, so we look at different types of plasmas. There's man-made ones here on Earth, as well as natural ones on Earth and in the universe. Right? So man-made plasmas, you have what's called plasma etching, which is used to make semiconductors that exist in pretty much all of our electronic devices. Right? So you could argue without plasmas, we wouldn't really have the information age we have now and all the technology we have. It's used to make lights, like high-intensity discharge lamps, for example. Plasma medicine is a relatively new field, using plasmas to do biological treatment, to affect biological things. Space propulsion, right, to get us to other planets. And of course, fusion experiments here on Earth. Right? Natural plasmas, you have lightning, space weather. So plasma makes up about 99% of the observable universe. Right? I say observable because if you follow physics, probably the majority of what makes the universe is dark matter or dark energy, things that we cannot see as of yet, right? But of the stuff we can see, 99% of it is in the plasma state. And most of this, or that 90%, it's all in space, right? It fills the interstellar medium between planets, between stars. It's what makes up stars, right? And so you have, black holes, astrophysical jets that shoot out high energy charged particles, and you have star-planet formation. Right? So how do we kind of characterize plasmas? And we kind of already talked about this, that we use the density of particles and then the energy of particles. So density, plasma density, symbol N, is generally counted in particles per volume, per cubic centimeter, per cubic meter. So this is akin to the density, mass density you may be familiar with, as just kilograms per cubic meter or slugs per cubic foot. For energy, we use temperature. Now, because a plasma tends to have 3 different types of particles, electrons, ions, and neutrals, we can often have 3 different types of temperatures. So temperatures of the electrons, of the ions, and of the neutrals. And oftentimes they are different from each other, sometimes very different from each other. Another property that is unique to plasmas is called a Debye length. And the Debye length can be thought of as a shielding or boundary layer distance or thickness for a plasma. Right? So most plasmas in the lab, which we call low temperature plasmas, tend to have these kind of properties, right? Where your ion temperature and neutral temperatures are about 1,000 Kelvin, which is still pretty hot, but much, much lower than the electron temperature, which is about 10 to the 5th Kelvin, or 10,000, 100,000 Kelvin. Right. And it's usually this very high electron temperature that makes these plasmas useful, because those electrons can do interesting things like produce new chemical reactions. So we'll talk a little bit about fusion, right? Fusion is probably the most publicly known or prevalent use or study of plasmas here on Earth, is to produce a star, right? On Earth, to produce our sun, to generate energy. And there are different ways to do fusion. So this is called inertial confinement fusion. And the schematic here is the National Nuclear Facility, NIF. The premise here is it uses laser beams, very, very high powered laser beams, to hit a target, which produces lots of high energy X-rays. Those X-rays hit a central fuel pellet to basically ionize it, and you can think of it, squish it until to high enough pressure where the atoms can fuse, and then it will explode and generate lots of heat and lots of energy. Right? And then you capture that energy to produce electricity. So that's inertial confinement, basically pushing the fuel together into a very small size in order for it to fuse. The other main concept of fusion is called magnetic confinement fusion, so tokamaks. So this is the ITER project that's being developed or being built in Europe. So tokamaks function differently. Instead of compressing a small target really fast with really high energy beams to create fusion, it creates a generally high temperature plasma that spins around this donut. And as the plasma spins around the donut, particles will run into each other, and it will cause fusion, release energy. And so it's more of a continuous process. At least that's the concept. And to prevent this hot plasma from basically melting the walls that it touches, there are very strong electromagnets that confine the plasma to keep it away from the wall. So it's sort of magnetic shielding, if you will, which is why it's called magnetic confinement fusion. So some fusion research is actually done here in the state at Auburn. So this is Auburn's fusion experiment. Right, so these large coils you see here are part of the electromagnetic coil structure that generates the magnets, and then this metal thing is the chamber where the plasma is held. And here is one of the investigators from Auburn, Dr. Dave Maurer, kind of crawling through the chamber doing some maintenance. So now let's talk about low temperature plasmas, probably the more useful side, at least for most things. So low temperature plasmas, it's less this, right? Less the sun, which has very high densities of 10 to the 31st particles per cubic meter and tens of millions of Kelvin, right? And more like this, right? Lower densities and lower temperatures. But in particular, it tends to have a large temperature difference between electron temperature and the ion or neutral or the heavy particle temperatures, because we really kind of want the energetic electrons to do stuff for us. So, all right, so high temperature plasmas, it's good to melt things, burn things, weld things, or or fusion. It's really hot, and that's about what you use it for. But that means you can't put your hand in a high temperature plasma. You can't put plastics, you can't put your cell phone or anything goes into it because it would just melt, right? For low temperature plasmas, we can actually use it for more applications and apply it to more things. Here are just some examples, right? You can use it for chemistry. So here's electron-induced reactions, right? Electron, it's a methane molecule and splits the methane into different things. Or a plasma causes plasma etching of some substrate, usually, for example, silicon. So this is how you make semiconductor chips for your cell phone or your computer. Or you can use plasma to create surfaces for attachment of molecules or for different chemical applications. And so now I'll talk about some of the examples of projects that we do and have done within the state, right? And this is all under the CPU2AL, which is a Connecting the Plasma Universe to Alabama project sponsored by the National Science Foundation. So it's a combination of computational experimental efforts, both and also theoretical as well as practical applications. And here's kind of the universities and industries that are part of the project. So we'll start big and go small, right? So big meaning astrophysical plasma, so space, right? So one of the projects is studying what is the behavior of the astrophysical plasma, especially the terminal shock between our solar system and the surrounding universe, if you will, right? So which is called the heliosphere and heliopause, right? And the termination shock is shown here in this graph. And this temperature shock is caused because the sun is constantly pushing outwards with a solar wind. A solar wind is a constant, you can think, wind or breeze of charged particles, of ions, electrons that the sun constantly emits, right? At the same time, the wider universe has particles in it. So with those things interact, you get this boundary effect between the two streams. And so the Voyager spacecrafts have crossed the termination shock. And so here's some data from Voyager back in 2007, and shows that at some point there's this sharp decrease in the velocity of the instruments that measure the ambient particles. And so one of the projects was looking at the Voyager data. So this is actual data from the Voyager probes, which were launched way back when, and are the farthest man-made things that have left the solar system, right, to study the astrophysical plasma and the termination shock for our galaxy, or for our solar system. Right. Coming down to Earth a little bit, there's also a study of the ionospheric plasma. So the ionosphere is a certain layer around the Earth that makes up the Earth's atmosphere, and it's full of charged particles, and it's what tends to create northern lights or borealis. Now, it's of interest because being charged particles, it will tend to absorb and diffract radio waves. So it makes satellite communications potentially difficult if there are regions of high density within the ionosphere. So understanding and modeling the density and the temperature and the behavior of the ionosphere is important for satellite communications. for example, your satellite TV. Right? And the ionosphere changes across the Earth, as shown here, as well as changes with the season and with the activity of the sun. So how do we study these things? How do we study the ionosphere? Well, one way and the main way is you launch rockets. You launch what are called sounding rockets up into orbit that cross the ionosphere, and those rockets have instruments mounted on them, and they take data as it goes through the ionosphere, and the data comes back down to scientists on Earth who analyze it to understand, okay, what is the behavior, what is the properties of the ionosphere that the rocket just traveled through. Another way to do it is you have low orbiting satellites. For example, here just schematically shown a bunch of small satellites like CubeSats, constantly mapping the ionosphere as they travel across orbit around the Earth. Right. Talking about satellites, right? Space propulsion, plasma space propulsion is also an area that we work on. So here, just some example. Here, just a random picture of a CubeSat, of a 6U CubeSat. Here are some thrusters, small Hall thruster, ion engines, and cathodes that have been developed by various researchers within the state. So space propulsion, plasma space propulsion, takes advantage of the fact that when you have ions, electrons, you can now use electric fields to accelerate them, right? So here's a basic schematic of an ion engine. So an ion engine, you create the plasma inside the plasma chamber, and you have grids which are biased such that it attracts the positive ions and accelerates into very, very high velocities, usually tens of kilometers per second, which makes it a very efficient propulsion system. Next, we can talk about dusty plasmas. So here now we're starting to shift from maybe science to some more applications. So dusty plasmas originated from, well, the concept originated from astrophysical studies, because way back when, in the beginning of the universe, planets, moons, suns first formed because individual dust grains started attracting to each other, started collecting and becoming bigger and bigger, until eventually they were big enough to have their own gravitational field, and they started pulling together. And so you get formation of planets. That's that way that all starts with individual interactions between dust particles, right? And these are dust particles in space, because space is full of plasma. It's a dusty plasma, right? So we can replicate this on Earth, for example, using a vacuum chamber. We create a plasma, and then we dump some dust particles in, and we see how they interact. So here's a video from Auburn University looking at oscillation of dust particles and motion of dust particles that are suspended within a plasma. And you can see they exhibit very interesting behavior. It also kind of looks kind of like a fluid, right? And so Auburn has what's called the MPDX experiment, which is a very high magnetic field experiment, where they're looking to study how does dust particles behave in very high magnetic fields, very high being multiple Tesla worth of magnetic fields. So for reference, the magnetic field of the Earth at the surface is about 50 Gauss, and there is 10,000 Gauss per Tesla. So 3 Tesla is a enormously high magnetic field. And some of the interesting things they found is by applying magnetic fields, you can control strongly how the dust particles organize themselves, right? For example, if you use a mesh electrode, such as this conducting mesh here, and you apply the magnetic field vertically, as shown here, the dust grains align with the mesh grids, right? And so this could be useful for producing very ordered structures and materials in the future. All right, so speaking of materials, plasma is also used to make superhard coatings. So for example, for implants, so here is a hip joint, artificial hip joint, right? It goes in your body. and it suffers wear and tear. Your hip joint, also your natural hip joint, suffers wear and tear, but your body naturally repairs that joint, the bones, but artificial ones, your body does not. And so you have to add coatings to try and prevent its degradation, but everything degrades over time. So 4 years later, here is this ball socket hip joint right here that has serious erosion, which means you have to replace these so often, which obviously is not fun for the patient or inexpensive. Right. So you want super hard coatings that do not break down. And if you look at sort of the material hardness scale, we all know that diamond is generally the hardest material known to man. But it turns out that being a really hard material does not necessarily mean it's great for coatings, right? Or good for a long life wear. So at UAB, they're investigating what's called SNOB, or CNOB, carbon, nitrogen, oxygen, boron materials. And they're forming these materials through what's called vacuum microwave PVCD. So vacuum microwave plasma chemical vapor deposition. So using a plasma to break down some gas and then taking the gas to depositably form materials. Right? So here's kind of a picture of the PVCD process going on inside the chamber. And what you get is you get different surface structures of the deposit materials, right? So these are at the roughly same scale. You can see very fine and much coarser and more faceted structures of the nanodiamonds. So what causes the difference between A and B here? Well, it's going to be the gas type, the plasma temperature and density that you're using. So there's a direct relation between the plasma and what you get out the end. Another way to generate materials is using atmospheric pressure plasma. So this is not in a vacuum chamber, right? So here are just some examples of nanostructures, nanoparticles created by atmospheric pressure plasmas, right? And it's been shown by controlling the plasma operating parameters, you can shift or control the relative size distribution of the particles, right, which has use for different applications if you need a certain particle size. So now onto the more biological applications of plasmas. So we talked about very briefly that you can treat surfaces with plasmas to improve chemical uses, chemical adhesion or bonding. So one application that UAB has investigated is plasma treatment of vascular grafts, so artificial vascular grafts, right? So vascular graft is if you have a clogged artery, right, and you need to bypass it, you can use a artificial graft made of non-reactive materials such as Teflon, right, that gets attached to the artery and so bypasses the clogged section, right? So, okay, squeamish picture coming up. And so the graft is simply just a tube, right? And the tube replaces the damaged portion of the clogged portion of the blood vessel. But one problem is the artificial tube, your body sees it, well, as an artificial structure. And it can cause what's called thrombosis, where the body sort of attacks it and causes it to form platelets and causes it to actually start clogging itself. Right? So the research focused on, can we make the material either less likely for cells to attach to, so less likely to clog, or more likely to attach blood cells and maybe grow its own internal cell structure, right? So we treated the treated the vascular graft with 2 different types of plasmas, and they found that it does indeed change the morphological structure of the surface that helps absorb proteins to prevent clotting, right, and favor cell growth. Now onto more, so that was using plasma to treat stuff that goes into living creatures. Now we can use plasma to directly treat living creatures, right? So plasma Biomedical generally go into two forms. One is sterilization. So here is a plasma jet treating a plated petri dish and essentially showing that the plasma can sterilize surfaces to prevent growth of bacteria, fungi, and even viruses. It can also, plasma has also been shown to improve wound coagulation speed, so speed up the rate which a cut closes and stops bleeding. Right? It's also being studied for treating cancer cells, treating tumors. Right? And so getting into this area of plasma direct biological interactions is very complex because you need to understand both the plasma physics as well as the biology. And biology itself is very complicated. And then the intersection of the two of them, right? Because the plasma can cause a lot of different things, right? It can cause cell apoptosis, which is programmed cell death. It can break DNA strands, it can crossing proteins. And this all happens because plasma creates lots of different things, creates electrons and ions, some heat sometimes, electromagnetic fields, light, UV radiation, but most of the time it tends to create what are called radical and chemical products. So those chemical species that are created, and a number of those species have biological applications. It can be absorbed by cells. So going away from bacteria and people, plasma also used to treat plants and food. So for example, here are some pictures of treating, I think, barley seed and pumpkin seed. We've also done multiple different seeds or different type of plants to improve the rate of germination and rate of growth. We've also looked at treating chicken skin or just poultry or meat as a way to sanitize and disinfect the surface of the food. And the plant treatment has shown remarkable results. So here's some work done by UAH and Alabama A&M, where it looked at treating turmeric roots for 60, 90, 120 seconds using an atmospheric pressure plasma. And we showed that with plasma treatment, there is a much greater growth, larger leaves, faster leaves, more leaves of the turmeric. And there is a larger yield, right? So the control is green here. And the max yield in red is almost 2x the yield of turmeric from the plant, right? All from a 90-second treatment of the turmeric at the beginning, which is a rather astounding result. And if this can be replicated across different crops, it can go a lot towards addressing food shortage issues around the world in the future. All right, then we have talks about plasma water treatment, right? So, dirty water or access to clean water is sort of a global issue in some places around the world, right? As well as for space exploration, right? So Scott Kelly drank 730 liters of recycled sweat and urine during his year in space. Right? And so here on Earth, we can, in your house, you can purify your tap water using water filter pitchers. On the International Space Station, they have this big rack system to purify their sweat and urine into drinkable water. Here on Earth, for municipal water, there are large water desalination and processing plants that produce our daily drinking water. All right. But expendable filters such as these are expendable, and large-scale desalination plants or processing plants are not really practical or economical in some cases, right? Especially in so plasma water treatment is an effort to look at, can we use the charged particles, the electrons, ions, and chemicals species produced by the plasma to break down contaminants in water? And it shows, yes, indeed we can. So here is a picture of a plasma jet, and then there is a little vial of blue water, so like these. So this blue is a methylene blue dye, which is a common dye used in biology as well as in textiles. Right? And it shows that with more treatment times, the methylene blue is basically broken down completely, and you recover water by itself. right? The blue dye is broken down into its constituent species, right? Now, there are lots of different ways to do water purification, right? Here's just some different ones. You can do a direct streamer, you can do bubbles, you can do liquid surface interactions. Here is a direct plasma jet that goes into the water, kind of like is shown here. Right? But kind of the amazing or interesting and useful results of all this work is plasma is shown to break down most, if not all, organic water contaminants, including PFAS, which is tend to call the forever chemical because it doesn't naturally break down in water, and its use has been kind of prevalent in the last 50 years, and there are very many instances of very contaminated water sources that we cannot remove with more traditional means. So plasma may be a possible solution to help this issue. So the low temperature plasma industry, all these things, applications I've talked about are currently being developed both in research labs as well as industry for actual applications. And there are a number of big and small companies, and here are just some of them who have developed these technologies for various applications. So the industry, the field, although may not be known to the general public, is growing surprisingly fast. Right? Now you may ask, okay, what do you actually need bare minimum to make a plasma? So really, you need three things, right? You need some kind of power source, right? And these can be really fancy ones or even really simple ones, like you can actually take a plasma globe, rip out the bottom power supply and use that. You can also find on the internet what are called plasma lighters, right? You'll need some sort of gas or something to create the plasma from, right? That could be a bottle of gas, or it could be just the ambient air around you, right? And then you need some kind of device with electrodes to deliver the energy into said gas. And these can take various forms depending on what your needs are. So it's, I'll say, relatively easy to create a plasma. And there are many YouTube videos you can find by different people which go into how to create circuits to generate plasmas. Right. So some final thoughts I have here. In my career, I've learned that plasmas are everywhere and actually used in a lot of things. Right? They're responsible for kind of our information age for semiconductors. And low temperature plasmas, turns out, have a huge range of applications and lots of interesting but complicated science to study. But because the applications tend to span from materials to plants to biology to space, it requires more than just plasma science to get the full benefit. It requires expertise and collaboration with biologists, chemists, material scientists, doctors, agricultural researchers, and many more. So it is a very multidisciplinary field. The kind of fun and sometimes frustrating thing about plasma science is it is not usually taught at the undergraduate level. So it's not really evident to students that this is an area of interest or even something that exists. Now, that's good in that almost every student coming into the field is kind of equally blind, right? So whether you come from an engineering program or a physics program or chemistry program, in terms of your plasma knowledge, you're probably all in the same boat. Right? And for me personally, it's been very exciting to discover all the new applications for low temperature plasmas. And I believe there's a very bright future for this technology and for the field, right? And then lastly, this is kind of what I've seen in my career so far. A plasma seemingly can fix all the problems, but it will ruin all the math because the addition of the electromagnetics makes everything complicated. But it's still interesting, fun, and can have useful and beneficial societal effects. Thank you.
All right, thank you so much, Dr. Xu, and thank you everybody that tuned in and listened to this very interesting PowerPoint and conversation. So thank you.
Thank you.
Hi, my name is Plasmy, and thank you for watching this video. Make sure to follow us on our social media. at CPE2AL on Facebook, LinkedIn, and Instagram. Bye!